Alright, we looked at arithmetic sequences and then followed that up with arithmetic series. Similarly, we just looked at geometric sequences, and now we'll take a look at geometric series. And recall that a series is simply a sum of all the terms in a sequence. So a geometric series is the sum of all the terms in a geometric sequence. Now, instead of starting with an example this time, I'm going to start straight in with the derivation of the formula for a partial sum of a geometric series. So let's say we're trying to find the sum of the first n terms of a geometric series. So t1 is the first term. The second term is t1 times r, the common ratio. The third term, again, you just multiply by r a second time, so you have t1 times r squared, etc. And this goes all the way out to the last term in the geometric series, which is t1 times r to the n minus 1. So if you have n terms, the final one is going to have an exponent of n minus 1. Another thing to note is that we are just finding partial sums here. These geometric series don't go on forever. We're just finding the sum of a few terms. Alright, so there's a little trick here. We can't do anything quite as nifty as with the Gauss example, where you can just write it in the reverse order. But there is a nice little trick that we can do with this to derive the formula, and that is to multiply this entire thing, both right and left sides, by r. So what do we get? Well, on the left side it's pretty straightforward. We would just have r times Sn. On the right side, the first term, every single one of those terms is going to get multiplied by r, so the first term is going to be t1r, and let's write that below the term that looks the same, t1r. And then the second term in the original series is t1r. If you multiply that by r, it becomes t1r squared. And of course, you're really just going to get all the same terms. The final term in the series is going to be t1 r to the n minus 1 times one more r, which is just going to increase the exponent by 1. So the one before that is going to look identical, and then the final one is just going to be t1r to the n. Now, what can you do with this? Well, you notice that all of these terms sort of in the middle are identical. And so if we subtract one from the other, we can get rid of all of those and just be left with a few manageable terms that we can manipulate. So if we take the top and we subtract the bottom, we get Sn minus r times Sn on the left-hand side. We get t1, and then all those other terms in the middle disappear, and all you're left with is subtracting that very final term, which is minus t, this should be t1 r to the n. So we have a nice little compact equation that we can work with to solve for Sn. The first step is to factor out the Sn on the left-hand side. When you factor out the Sn, you get 1 minus r. Right, you can verify that's correct just by expanding that. Sn times 1 is Sn. Sn times r is r times Sn. On the right-hand side, we can do a similar factoring. We can take out a common factor of t1, and that leaves us with 1 minus r to the n. So now all we need to do to get Sn on its own is to divide both sides by what's in the brackets there, 1 minus r. So we get t1 times 1 minus r to the n all over 1 minus r. And this is the formula that's generally given for the partial sum of a geometric series. There's an alternative way to write it, which just involves sort of flipping the two binomials. If you have a minus b and you flip it to make it b minus a, all you're really doing is taking out a factor of negative 1. Well, if you take out a factor of negative 1 from both the numerator and the denominator here, you can rewrite this as Sn equal to t1 times r to the n minus 1 over r minus 1. And the reason I write this alternative version is because sometimes it's a little bit more convenient to use this given that both binomials are going to be positive. Most of the time when you use the original formula, 1 minus r to the n and 1 minus r are both going to be negative. And then you get this negative over negative becomes a positive, but it just leads to the potential for some arithmetic mistakes. Okay, so let's take a look at a few examples. Let's say we have a sum of a geometric series, and it's 10 plus 20 plus 40, etc. So there's your geometric series. Each term forms a term in a geometric sequence. And if we want to find S8, in other words, the sum of the first 8 terms here, we can just basically plug the numbers into the formula. The first thing, though, we need to do is figure out what r is. What's the common ratio? So to find the common ratio, you just take any term divided by the previous one. So in other words, 20 divided by 10 or 40 divided by 20, whichever your preference, you get 2. So t1, the first term, is 10. 1 minus r to the n is 1 minus 2 to the power 8, all over 1 minus 2. So here's the example where it'd be a little bit nicer just to use that alternate formula, because then you can write this as 10 times 2 to the 8 minus 1 over 2 minus 1, and we don't have to worry about the negatives. 2 to the 8 is 256, so we have 10 times 256 minus 1 all over 1, and this is obviously just 255 times 10, or 2,550. Okay, let's take a look at a second example. Let's say we have a series that is 7 minus 21 plus 63 minus etc. And we want to find S5, the sum of the first 5 terms of this series. Again, the first step is to find r. The terms are flip-flopping between being positive and negative, so you know that r is negative. Negative 21 divided by 7 gives you negative 3. Alternatively, 63 divided by negative 21 gives you the same thing. So here we have 7 times 1 minus negative 3 to the power 5 all over 1 minus negative 3. So for this one, actually it makes sense just to use the formula as it is. And keep in mind that when you raise a negative base to an odd exponent, it stays negative. So we have 7 times 1 minus negative 243 all over 1 minus negative 3, which is the same as 1 plus 3, which is 4. And 1 minus negative 243 is the same as 1 plus 243, which is 244. So we have 7 times 244 all over 4. We can take out a common factor of 4, and we get 7 times 61. So this is 427. All right, 2 more quick examples. Example 3. Let's say we have a series 80 plus 40 plus 20, and we want to find S10, the sum of the first 10 terms. Well, the first term is 80. What's the common ratio? Take any term divided by the previous one, so 40 divided by 80 is your common ratio, which is a half. So we have 1 minus 1/2 to the power 10 all over 1 minus a half. And again, here it's okay to leave this the way it is instead of using the alternate version, because the both of those binomials are going to be positive. So what do we get here? We have 80. A half to the power 10 is really just 1 to the power 10 over 2 to the power 10. 1 to the power 10 is obviously 1. 2 to the power 10 is 1,024. So this is 1 minus 1 over 1,024. And 1 minus a half is just a half. 1 can be written as 1024 over 1024. So this is really the same as 80 times 1023 over 1024, right? That's 1 minus 1 over 1024. When you divide something by half, it's the same as multiplying by the reciprocal, in other words, multiplying by 2. So we have really here 160 instead of 80, because we're dividing by half, times 1023 over 1024. And we can cancel out, there's a common factor of 32 there. And we take out that common factor of 32 from both 160 and 1024, and we get 5 times 1023 over 32, which is 5115 over 32. Now I've given it as the exact form, which is nice, but for most of these you're going to be reaching for a calculator and getting a decimal approximation. In this case, the decimal, not approximation, the actual value is 84375. So 159.84375, or if you reach True Calculator and you rounded it to 159.8, it's probably going to be good enough in most cases. Let's take a look at one more. Example 4 here. Let's say you're told you have a geometric series, and you know that the sum of the first 10 terms is this big number here. That's one thing about geometric sequences and series. The numbers get pretty big sometimes. So we have 4,543,825. You're given R as 4, and then the question is, what's the first term? So go ahead and look for the formula. The sum of the first 10 terms is the first term times 1 minus r to the 10 all over 1 minus r, and we're given r as 4. So this is t1 times 1 minus 4 to the 10 all over 1 minus 4. And we're told that this is 4,543,825. So 1 minus 4 is negative 3. Here's our equation. Our equation is right there. The only unknown is t1. So we can multiply both sides by that denominator, negative 3, and divide both sides by 1 minus 4 to the 10. 4 to the 10 is a huge number, which you're going to be reaching for a calculator for. In fact, this is one where you pretty much do the whole thing on the calculator. So t1 is negative 3 times 4,543,825 all over 1 minus 4 to the 10. And you just punch it into the calculator, and you get a nice small number, 13. Okay, actually I lied. There's one more example, example 5. So example 5 is a little story that I heard when I was younger. I tried to find the source of this before this lesson, and I couldn't find it online. So if you know the source, please let me know. And it's a story about a wealthy king in this land, and he wants to hire a brick maker to build a wall around his garden. So he offers the bricklayer, $1 a brick, or 1 gold piece a brick, something like that, to build this brick wall. And the bricklayer says, well, I've got a better deal for you. I will, so we have a brick wall. I will build your wall for you, and the first brick will only cost you 1 cent. And then the second brick will cost 2 cents. And every brick thereafter will just simply cost double the brick before. The third brick will be 4 cents. And so, for instance, the total for the first 3 bricks is only going to be 7 cents. And that way you'll save some money. So the king says, all right, I'll hire you to build a brick wall. Now, you can sort of see where this is going. Most brick walls are going to have a lot more than 30 bricks, but let's just, for argument's sake, find out how much would it cost to build a brick wall with 30 bricks. So how much would it cost to build a 30 brick wall? So what are we looking for here? We're really looking for S30. And what's the first term? Well, the first term is a penny, 0.01. The formula says 1 minus r. So what's the common ratio? We're doubling each time, so the common ratio is 2. 1 minus 2 to the 30 all over 1 minus 2. And here's an example where the alternate version is nice because you can eliminate the negatives. So 2 to the 30 minus 1 over 1. And probably going to be reaching for your calculator to do 2 to the power 30. It's a very big number. And you find out that this tiny little 30 brick wall, which started off at such favorable terms for the king, ends up costing $10,737,418.23. Needless to say, the king is not too happy to pay this extraordinary sum, and instead of paying this sum, just chops the head off of the bricklayer. At least that was the version of the story I heard when I was younger. I'm not entirely sure what lesson was supposed to be imparted there, but that's how the story ended in my version. Okay,